Okay, problem number 13. We've got x squared y minus xy squared is equal to 4, and we're asked to find what is dy dx. All right, let's do implicit differentiation. Let's take the derivative of each side with respect to x. Okay, and let's note here that as we do this, what do we got? We have a difference, so there's one rule. We've got a product, two products. And then whenever we take the derivative with respect to x of y, we are going to end up with a chain. So we've got lots of rules here. Do me a favor, in your homework, write big. Don't try to squeeze it in here to save paper and then end up making a small mistake because the problems get so complex. Right there. So, doing this term first. First times the derivative of the second plus the second times the derivative of the first. And there's that part done. Switch colors for that part. Minus the quantity. Because this is going to be using the constant multiplier rule. Minus the quantity. First times the derivative of the second plus the second times the derivative of the first. See how careful I was with that secret agent?
Secret agent, man.
Something about taking away your name. I'll have to ask Mr. Zurid. He'd know. Whether it's the secret agent man. All right. Now what? Let's clean it up. X squared dy dx plus 2xy. Let's expand this out. Negative 2xy dy dx minus y squared. And now it's time for the separate. Everything with dy dx, let's keep on the left-hand side. Everything that's not, let's push over to the other side. So x squared minus 2xy dy dx is equal to y squared minus 2xy. Double check my algebra, please.
Correct.
You're good? All right. Oh, I forgot. Right here. There's the error. I lost that dy dx when I transcribed it. All right. Continuing on then. Dy dx times 2xy is equal to y squared minus 2xy. And now we're ready, big and blue, to write our final answer. Dy dx is equal to y squared minus 2xy, all divided by x squared minus 2xy. And then, by the way, before I do that, before I say my really final answer, let's go up there and look again. Are there any nice substitutions to make? No. Does that have the convenience of being the right answer?
Two. Maybe.
Yes. It is in the back of the book.
Yes.
What were you basing that no on, Phil?
I have no idea.
Is it possible,
Random word.
Mr. Fedor, is
First
it
thing.
possible to cancel the negative 2xy or not?
No.
No.
Okay. No. Well, I mean, come on. I mean, that's like saying, hey, you know, I got 2 plus 2, and I've got, now let me make a better example. I've got 3 minus 2, and I've got 4 minus 2. Can I take this thing that's clearly 1/2, and can I wipe those out and get 3/4?
No. If they were multiplied, you could.
No. So don't do that. All right.
So now the problem is where something.
Where's the slope defined?
Oh, where's the slope defined? Okay, great. Thank you for reminding me about this other part. We found the derivative. Now we have this other part saying, okay, slopes aren't defined everywhere. Remember we had corners and cusps, discontinuities, and vertical tangents. Now, going back to our original function, there are no places where this function is going to be discontinuous.
Good.
All right? So that's good. All right? By the way, things in this polynomial form, they're always smooth. They don't have corners or cusps. So we're good there. The only thing that we have to watch out for is vertical tangents. Vertical tangents occur when the bottom of our derivatives are undefined. So where is it defined? Where x is equal to, okay, it's not, let's write it out, it's easy to probably, it's not defined when x is equal to 0. By the way, I can also take this out, I'll take an x out and I get x minus 2y.
So when x equals
Or when x
equals 2y.
is equal to 2y. Now, because what I did was I set x equal to 0, and I took this other multiple, and I set it equal to 0. And when I solve for x here, that 2y goes over the other side. Yeah. All right. So, this one, x can't be 0. This one, we don't know where there is a possible location where x and 2y exists. It may not exist on this curve. How do we check? Well, we have a substitution here. Every place you see an x, replace it with 2y, and we end up getting, in our original equation, if I take this substitution, I would get 2y squared times y minus 2y times y equals 4. Sorry, y squared, thank you. So we end up with 2y cubed minus 2y cubed equals 4. So for what values of y is that going to be true? Never. I just got 0 is equal to 4. That is never true. Do we have to worry about this case? No. So the only place where it's not defined is when x is equal to 0.
What about because we also have like y equals stuff.
Oh, well, I think what they're going to... Actually, you know what? X can't be 0 either. X can't be 0. If I try to put x equals 0, I get 0 minus 0 equals 4.
Not equal.
So,
That's why it's not.
so we found, here are the two places where it could have crashed and burned. Both of these things never happen. There are no places that this derivative doesn't exist. All real numbers. Sorry, all places on the curve. Because remember, now we have x's and y combinations, not just x's. Kaylin.
The book said y does not equal x over 2. That's the answer?
Don't just try to make everything as a point.
I don't remember.
Okay,
That makes sense.
you're looking at, what is this, 13?
Mm-hmm.
Okay, let me look in the teacher's edition so I don't have to turn all the way to the back. 13. Okay. Okay, it says what we have, except it has what we have, except that it has this. Our answer is algebraically equivalent to theirs.
Mm-hmm.
Not a problem. And then they mention these two things, right? They say it's not for every point except when x is 0 or y is equal to half x, which is the same thing as what we have. What did we do? We went one step further and saying, is there any places where this is true? No. Is there any places where this is true?
Why didn't they do that?
Because
Or
because
maybe.
we're better.
Okay.
We're more thorough.
But if we're not defining we
Okay.
have to do that.
I'm sorry, Ian?
Wait, like
Do you have to do what we just did?
Yeah.
I think it makes for better mathematics.
on our test will we have to?
Maybe. Yeah.
Yeah, I mean, if I'm modeling good behavior, if I'm modeling good math behavior, then yeah, this is exactly what I want you to do. All right?
And so we're trying to prove that those points aren't on the graph, or what?
We've already proved that they're not on the graph.
So what do we?
So there are no points on this curve where the derivative is undefined. Is what my final conclusion is. There are no vertical tangents. All right. So that was 13. Should we do 15 now? We shall. So number 15. The new curve is y cubed. Oh, I'm sorry, x cubed plus y cubed equals xy. Ready? Tell you what. You instruct me now.
Take those derivatives. 3x squared.
Okay, wait.
plus-
Take the derivative of both sides. One person at a time, though, because otherwise the recording is going to sound really muddled. And because your classmates aren't going to get much out of it. Someone say, here's what I'm doing, and here's my result. Billy, you want to help me out?
Sure. So, derivative of x cubed is 3x squared.
Great. Popcorn somebody.
Anybody but
Charlie.
Okay, so now you have a chain rule with y, so it's going to be 3y times dy dx.
Isn't it 3 by
3 by
I'm
squared.
sorry, 3y squared times dy dx.
What about this thing in here?
Plus.
Okay. Charlie, popcorn somebody.
Ian.
and then you take the derivative of x and y and use the product rule.
Okay, go ahead.
First, which is x, times the derivative of y, which is dy dx, plus y times the derivative of x, which is 1.
Okay.
Top one, Lucy.
I'm going to time out here. Lucy, you are next. But I want to say something. How many times have you done the derivative of xy so far?
Million.
A million?
Whoa.
A million.
That's kind of.
Emma, a million? Million.
How much shape
Okay. By the way, what you're going to notice is that in certain ones of these you keep on doing, it's always the same answer.
Identity.
So what ends up happening is that you see this and you don't even start thinking product rule anymore. You just say x dy dx plus y. Okay. As you do that, as you get more comfortable with these, those automatic responses are going to happen. Lucy, you've been popcorn.
Okay. You subtract y to the other side, and then you subtract 3y squared dy dx to the other side.
So you're going to subtract y from both sides, and you want to subtract this?
Yeah.
Okay, and what's the net result after you're all done, Lucy?
3x squared minus y equals dy dx x minus 3y dy dx.
0 squared.
Okay. Popcorn.
Okay, then you take the derivative, the dy dx out and have it dy
Isn't
dx.
there supposed to be a square in there?
Yeah.
Yeah,
Did we lose something?
3y squared.
Y 3y squared.
There we go.
So,
So take the dy dx out.
and then it's dy dx x minus 3y squared. That equals 3x squared minus y.
Okay, who's going to finish it off?
Okay, so then you divide the right by x minus 3y squared. Divide like both sides by that, and then you get dy dx.
Is there a pattern here that these happen to be like X and Y?
Similar.
Yeah. It's like 3x squared.
Sure, it certainly,
minus
with
y.
these group of problems, it certainly seems to be it pops up a lot. Okay, great. So now let's finish up the job. Are there any values where this derivative doesn't exist?
Y squared equals x over 3.
Okay, so the derivative doesn't exist where this bottom is 0, and I could just put that in that form. Now, are there any points on that curve that are on that curve? I don't know.
Let's graph it.
Yeah, that's the hard part. Since these are not easily put into y as a function x, and they're also easily not put into parametric mode, it's actually very difficult to find out whether, well, this isn't hard to graph, but it's hard to graph this. I'm not even sure what that curve looks like off the top of my head. Okay, it's not your typical conic section.
Something like that.
Well, certainly we had an example in the homework the other day where it was that loop to loop. Yeah. So we'll just say it doesn't exist if that's true. And we'll leave it there. All right? That's good? That's 15? Okay, let me, no.